Hello and welcome to my virtual March Meeting 2020 talk on gauge theories for the thermal Hall effect. My presentation is going to be about some of our recent theoretical efforts with main references given here at the bottom to understand the thermal Hall effect in doped and undoped quantum magnets. Our study will go beyond the conventional spin wave analysis and, as we will see, is very conveniently described by abelian and non-abelian gauge theories with interesting properties. But before starting, let me acknowledge my collaborators. The results have been obtained together with Subir Sachdev and two graduate students at Harvard, Ryan Samajda and Hao Yugu. We also had help from California by Shubayu Chatterjee and Chen Kishu. To make sure we are all on the same page, the thermal Hall effect arises once mobile degrees of freedom, here mobile in the xy plane, are driven through the system due to a temperature gradient, and a magnetic field is applied along z, leading to a heat current along the third perpendicular direction. The associated thermal Hall conductivity, kappa xy, relates the temperature gradient to the heat current as shown. Measuring kappa xy is a very powerful experimental tool because it allows to probe charge-neutral excitations and because it is sensitive to the Berry curvature, or at sufficiently low temperatures, even the Chern number of the bands of the degrees of freedom that dominate heat transport in the system. For these reasons, the thermal Hall effect has gained a lot of attention in the condensed matter community in recent years, most notably in the context of spin-liquid candidate materials such as ruthenium chloride. On a very general level, one of the key points I would like to make is that the magnetic field, which we apply to probe the system via the thermal Hall effect, can have a much more significant impact on the system than one might naively think, at least under certain circumstances. To illustrate this, consider the Heisenberg model with spin operators Si on the sides I of the lattice of the system and exchange couplings Jij. Let me emphasize right away that we will neglect spin-orbit coupling throughout this talk. The application of a magnetic field gives rise to a Zeeman term, but also to an orbital coupling, which to leading order in a T over U expansion yields this term. It involves the triple product of spin operators located at the edges I, J, and K of the elementary triangles of the system. To isolate the consequences of the orbital coupling, we will neglect the Zeeman term in the following, but we will come back to it later. For concreteness, let us first discuss the triangular lattice shown here on the right, with nearest neighbor J1 and next nearest neighbor J2 exchange couplings. The orbital coupling J chi is associated with the elementary triangles such as the one shown here in orange. The phase diagram of the model, as obtained via exact diagonalization, is shown on the left as a function of J2 over J1 and J chi over J1. We note that besides several magnetically ordered phases, there is an extended regime shown in light blue where a chirospin liquid phase is stabilized. In particular, there is a finite range of J2 over J1 where the critical value of J chi to enter the chirospin liquid phase is very small, in agreement with other numerical estimates of this critical value. There are similar results for the square lattice Heisenberg model, again with nearest J1, next nearest J2 exchange couplings, and orbital coupling J chi with elementary triangles such as the one shown in orange. As computed in the paper at the bottom of the page, its phase diagram is shown on the right, where two angles, phi1 and phi2, are used to parameterize the system according to the relations down here. Roughly speaking, you can think of the horizontal axis as the J2 axis and the vertical axis as the J chi axis. Again, we observe an extended regime where a chirospin liquid is stabilized and a range of J2 where the critical value of J chi is very small. Taken together, we see that, at least for certain parameter regimes, the impact of the orbital coupling is way more significant than one would naively think based on its numerical value. As a magnetic field is necessarily present in the thermal Hall measurements, it seems important to ask, how does this affect the thermal Hall conductivity? In particular, when driving the system in proximity to a chirospin liquid, does this allow for an enhancement of kappa xy? Now, in the remainder of the talk, I will first discuss in detail the enhancement of the thermal Hall conductivity when the magnetic field drives a magnetically ordered phase in proximity to a chirospin liquid, focusing on the square lattice antiferromagnet for concreteness. In this first part, we will concentrate on the key physics and the temperature and magnetic field dependence of kappa xy. The second part will be more technical and will deal with the underlying gauge theory and will identify an interesting emergent global SO3 symmetry. We will also discuss that the theory is believed to have 4 dual field theoretical formulations and reconnect all of these dual descriptions to the lattice magnet. As an interesting application of these dualities, I will, in the last part of the talk, briefly summarize a recent work where we approach the demanding problem of generalizing these computations to the doped system, where on top of the spin degrees of freedom, we also have to deal with mobile electronic charges. To get started with the first part of the talk, let us revisit the J1, J2 Heisenberg model on the square lattice. Setting aside recent controversies that are irrelevant for the following discussion, its phase diagram as a function of J2 over J1 looks as shown. At small values of J2, we have the conventional Néel state. At intermediate values, a valence bond solid or VBS phase, characterized by the spontaneous formation of singlets along the indicated ellipses, arises, and at larger J2, yet another magnetically ordered phase emerges. Since we're interested in the physics close to the Néel state, let us focus on the Néel and VBS phases and the transition in between the two, which, at least in a large intermediate range of length scales, is characterized by a deconfined quantum critical point and an emergent global SO5 symmetry that mixes the 3 components of the Néel order parameter with the 2 of the VBS state. There are several likely equivalent descriptions of this critical point. In the interest of time, however, let me only point out the one shown here, which involves 2 Dirac fermions, Fv, in 2+1 dimensions, coupled to an SU2 gauge field A mu. I emphasize this description as it exhibits the SO5 symmetry as an explicit symmetry, and since we will come back to it multiple times during this talk. But first, let us next revisit the impact of the orbital magnetic field associated with the J chi term introduced earlier. The key question is, how does the phase diagram look like once we add J chi as a second axis to it? Based on the numerical studies mentioned before, we expect the chiral spin liquid to show up, and in combination with field theoretical arguments, conjecture the following phase diagram. First of all, we assumed that J chi is a relevant perturbation to the critical point. That is, the system immediately enters the chiral spin liquid when turning on J chi at the critical point. This is in fact natural from the point of view of the aforementioned critical theory, since J chi assumes the form of a Dirac mass, M chi, in that field theory, and hence is expected to be relevant. Of course, if we start away from the critical point, say here in the Néel state, a critical value of J chi has to be applied in order to enter a phase where the chiral spin liquid coexists with Néel order, before eventually reaching a pure chiral spin liquid. We expect similar behavior on the VBS side of the phase diagram, albeit less relevant for the following discussion. Note that we further assume that J chi is a more relevant perturbation than detuning J2 from its critical value, in agreement with the scaling dimensions deduced from the field theory in the limit of a large number of fermion flavors. This leads to the superlinear form of the phase boundaries, and most importantly implies that the critical value of J chi to enter the chiral spin liquid coexisting with the Néel phase increases only very weakly as a function of detuning J2 from its critical value. Consequently, we believe that the experimentally accessible values of the orbital coupling can drive the Néel state in proximity to a chiral spin liquid phase. This renders spin-on excitation relevant and leads to an enhanced thermal Hall effect, even if the system never crosses the phase transition. We next demonstrate this enhancement using an explicit model of the transition, which we construct in the fermionic spin-on description. For those of you who are not familiar with this technique, the idea is to rewrite the spin operator in terms of auxiliary fermions, the spin-on operators F, where sigma are Pauli matrices, and an additional constraint is imposed to avoid enlarging the Hilbert space. Due to an internal redundancy of this reparameterization, we will eventually end up with a gauge theory. The easiest way to see this proceeds by defining a 2x2 matrix F containing the spin-on operators. It requires only straightforward algebra to convince yourself that the expression for the spin operator can be rewritten as a trace in this way, and is hence invariant under right multiplication of F by an arbitrary site-dependent SU2 matrix, leading to an SU2 gauge theory. But before discussing the full gauge theory, let us first illustrate the key physics starting from the effective mean field lattice Hamiltonian that we obtain. It contains terms describing hopping of the spinons on the square lattice. As can be seen on the right, there are nearest neighbor hopping terms, T1, with pi flux on each plaquette. At low energies, this leads to the SO5 symmetric description of the critical point in terms of the two Dirac fermions mentioned above. In our case, however, we have to add the orbital coupling of the magnetic field, which yields next nearest neighbor hopping amplitudes shown in red and with magnitude T2. Furthermore, we will add the Zeeman coupling of the magnetic field as promised earlier, and a term that describes the presence of long-range Néel order. Let us next discuss the resulting phase diagram of this model, which is shown on this slide as a function of orbital magnetic field and Zeeman coupling at constant non-zero value of the Néel order parameter. You can see that there are two phases, and to understand their properties, let's take a look at this one-dimensional cut of the spin-on band structure for parameters corresponding to the blue dot in the phase diagram, where I also indicate the Chern numbers of the occupied bands. In the present case, the net Chern number of the occupied bands is 0. Therefore, the effective action of the gauge fields does not contain a Chern-Simons term, leading to confinement at the longest length scales. Consequently, this phase is just a conventional near state. If we increase T2, we will move towards the phase boundary, and at the phase boundary, the gap will close. If we increase T2 further, it will reopen, but note the Chern numbers have changed. Now, the net Chern number of the occupied bands is non-zero, thus implying a Chern-Simons term in the action of the gauge fields, which prevents confinement and leads to a chiral-spin liquid, which by construction coexists with Néel order in our case. Having established the phase diagram, we will next discuss the physical quantity we are most interested in, the thermal Hall conductivity kappa xy. We have computed kappa xy in leading order in an expansion in inverse number of fermion flavors, which is equivalent to mean field theory for the current fermionic description. Kappa xy over T in natural units can be expressed as an integral over energy epsilon involving f prime, the derivative of the Fermi function, and the dimensionless hypothetical Hall conductivity sigma hat of the spin-on states below energy epsilon. The computed thermal Hall conductivity, first for Néel plus chiral-spin liquid state, as indicated by the green dot in the phase diagram, is shown here at the bottom. You can see kappa xy over T as a function of temperature. It is found to increase with decreasing temperature, and at T equals 0, which is a value determined by the indicated quantization condition that involves the Chern number Cn of the occupied bands. If we decrease T2 a little, corresponding to the orange dot, you can see that the temperature profile of the thermal Hall conductivity is slightly altered, which reaches the same value at 0 temperature since we remain in the chiral-spin liquid phase. Let's decrease T2 further and further. Now we are at the phase transition such that if we decrease it a little bit further, we are on the other side of the transition, but still very close to it. And the associated thermal Hall conductivity corresponds to the lowest curve on the right in dashed blue. We now reach 0 at 0 temperature as required by the quantization condition. However, we see that at elaborate temperatures, the thermal Hall conductivity behaves very similar to that of the chiral-spin liquid, despite the system being in the trivial phase. This is precisely the enhancement mechanism that I mentioned earlier. Finally, if we decrease T2 further, we move away from the phase transition and the magnitude of the thermal Hall conductivity decreases. Next, we turn to the magnetic field dependence. Note that a physical magnetic field will change T2 and BZ at the same time, which means that increasing a magnetic field will correspond to a one-dimensional trajectory in this two-dimensional plane. For simplicity, let us take straight lines and discuss possible slopes separately. If the trajectory is like this, the resulting kappa xy over T will have the dependence on physical magnetic field plotted here for different temperatures, from low to high. As you can see, the field dependence is almost linear, but the overall magnitude is low, since we are quite far away from the transition. For a very small slope, such as the one indicated in the phase diagram, the behavior looks like this. But the largest signal is obtained if the system stays close to the transition line for an extended range of magnetic field, as is the case for this line, with resultant behavior shown down here, which is almost linear in magnetic field but curves down a bit at larger magnetic fields. So far, we have mostly focused on the phases of the system and their thermal Hall conductivities. Let us next, in the second part of the talk, discuss the underlying field theory in more detail. As you might have expected, based on the band structure of the spin-ons, the field theory will involve Dirac fermions. Let us be more specific. The Dirac matrices gamma mu act in sublattice space, which is the space we had to introduce in order to diagonalize the pi flux Hamiltonian via Fourier transformation. The SU2 gauge fields A mu act in valley space, that is, in the space spanned by the two Dirac cones you can see on the right. As spin and valley are locked, you may alternatively think of this as acting in spin space. Furthermore, there's a mass term, m, that changes sign across the transition. While one might naively think that the heavy fermions in blue and red in the band structure on the right can be ignored at low energies, this is not entirely true, as the bands carry Chern numbers, which leads to a Chern-Simons term at level -1/2. Let us next connect the Lagrangian to the SO5 theory consisting of two Dirac fermions, Fb. As already mentioned before, the orbital coupling J chi corresponds to a Dirac mass term. While this term preserves the SO5 symmetry, the additional mass term associated with Néel order reduces this symmetry. Recalling that the Néel order parameter is part of the SO5 manifold, choosing one direction for the Néel order reduces SO5 to SO4. Among the remaining 6 generators of SO4, 3 generators act in the space of heavy fermions with mass given by the sum of the absolute values of m chi and mn, and are thus irrelevant at low energies. The remaining 3 generators act on the light fermions with mass given by the difference of the masses, and generate an SO3 symmetry. Let me emphasize that the symmetry is not related to spin rotation invariance, which is broken explicitly, or any microscopic symmetry for that matter, but instead is an emergent symmetry in the vicinity of the critical point between the Néel and Néel plus chirospin liquid phase. We have worked out explicitly which combination of field operators transform into each other under the emergent SO3 symmetry. Unfortunately, the interpretation is not as straightforward as in the case of the SO5 critical point, and the simplest combination of lattice spin operators with the same behavior under all microscopic symmetries of the system as the field operators transforming under the emergent SO3 are shown here. The only intuition I can provide is that 2 of them have a spin-orbit coupled nature, which is related to the fact that valley and spin are intertwined in the band structure of the spin-ons. Another interesting aspect of this field theory, which I abbreviate here as SU2 Chern-Simons at level -1/2 with a single fermion doublet, is that it has been studied in the high-energy literature recently and is believed to not only have 2, but in fact 4 different dual formulations. The other 3 field theories are an SU2 Chern-Simons theory at level 1 with a scalar that is a bosonic doublet, a U1 level 2 theory with a scalar, and a U1 level -3/2 theory with a fermion. These theories are believed to flow to the same renormalization group fixed point and thus are all characterized by an emergent SO3 symmetry. Remarkably, all of these field theories have a condensed matter parent. While we have already discussed a possible microscopic origin of the first field theory arising from the fermionic spin-on description of the antiferromagnet, it will be convenient for the doped case to take a more general perspective that allows for charge degrees of freedom. To this end, we will first assemble the electronic operator C, carrying both spin and charge, in a 2x2 matrix as shown, and rewrite it as a product of 2 2x2 matrices. The matrix F, containing the fermionic spin-on operators as before, and an SU2 matrix R with bosonic charge on fields B. The SU2 gauge symmetry corresponds to left multiplication of R by an SU2 matrix B, and as before, right multiplication of F by V dagger. Since rotation in pseudospin or particle Hall space corresponds to right multiplication of R, we can think of this reparametrization as a transformation in a rotating reference frame in pseudospin space. An alternative way of fractionalization proceeds by rewriting the matrix C of electronic operators as R times psi, that is, in the opposite order as before. Here, the SU2 matrix R contains the bosonic spin-on operators, carrying spin but no charge, and psi the fermionic chargens carrying charge but no spin. Gauge transformations now act in the way indicated here, but more importantly, upon noting that spin rotations correspond to left multiplication of r while acting trivially on psi, the reparametrization can be thought of as transforming to a rotating reference frame in spin space. At low energies, such an approach gives rise to the second dual field theory. Due to time constraints, I would just mention that the remaining two field theories can be related to a composite boson and a composite fermion description of the transition. And with this, I come to the last part of my talk on the doped system. The first question we have to ask is, which approach is most convenient for describing the additional charge degrees of freedom? In the context of the cuprate superconductors, with minimalistic phase diagrams shown here on the right, the impact of doping on mod insulators, with nail order in this case, has been discussed in detail and is known to give rise to the so-called pseudogap state before, at larger hole doping P, a conventional Fermi liquid emerges. The approach for transforming into a rotating reference frame in pseudospin space, which we used for the undoped system and involves fermionic spin-ons, is not convenient in this case. This is due to the fact that the chargens are bosons and hence are difficult to reconcile with experiments indicating that the charge degrees of freedom in the pseudogap phase show Fermi liquid behavior. Instead, the second dual theory discussed above, which can be thought of as transforming into a rotating reference frame in spin space, is more natural because it involves bosonic spin-ons and fermionic chargens, which can form Fermi surfaces. In fact, for this reason, we have been studying this approach in detail in the last few years, and, for instance, shown that it naturally gives rise to Fermi arcs as seen in photoemission experiments. We have also successfully compared predictions of this theory with dynamical mean field theory and quantum Monte Carlo computations on the Hubbard model, and found good agreement with new high-resolution photoemission data on an electron-doped cuprate compound. In this formulation, the pseudogap is related to a Higgs mechanism. The Higgs field, Hi, is defined in the way shown here, where phi is the Hubbard-Stratonovich field used to decouple the Hubbard interaction with, or more generally represents the collective spin mode in the spin-fermion model. Based on our previous discussion, you can intuitively think of the Higgs field as the spin degrees of freedom transformed into a rotating reference frame. When the Higgs field condenses, it gaps out the chargens at pi0, leading to small chargon pockets and ultimately to the Fermi arcs shown on the previous slide. The effective non-relativistic chargon Lagrangian that we use to compute the thermal Hall conductivity with is shown here. It involves the residual gapless emergent gauge field or emergent photon, lowercase a. And the gauge field, uppercase a, represents the external magnetic field. Let us next first neglect the emergent gauge field. In that case, the Wiedemann-Franz law is obeyed and kappa xy over t is proportional to the charge Hall conductivity as shown. To study the contribution of the photon, we use the following simple effective action that is expected to arise when integrating out the chargens and the gapped spin-ons. Besides the Maxwell term, it contains a Chern-Simons term with prefactor related to the Hall conductivity of the chargens. We have computed its contribution to the thermal Hall conductivity in the limit of a large number of fermion flavors. To cut a long story short, the most important result is that the additional contribution to kappa xy coming from the gauge field has the opposite sign of the Wiedemann-Franz part. This means that when entering the pseudogap phase from the Fermi liquid, an additional contribution is expected to arise that reduces kappa xy from its Wiedemann-Franz value. And with this, I'm at the end of my talk, which I would like to summarize. So in the first part of the presentation, we discussed the thermal Hall effect in undoped quantum magnets, noting that for certain parameter regimes, the impact of the orbital magnetic field can be significant. We have seen that it can drive magnetically ordered phases, in our case the near state, in proximity to a chiral spin liquid, which enhances the thermal Hall response. We have also shown that the low-energy field theory in the vicinity of the transition to the chiral spin liquid phase has an exotic emergent SO3 symmetry and has not only one, but in fact 4 dual descriptions in terms of abelian and non-abelian gauge theories. The second part of the talk dealt with the doped system. Here we analyzed a theory motivated by several previous theoretical and experimental works in the Kuiper superconductors and related to one of the 4 different dual field theories of the first part of the talk, which consist of fermionic charge-ons coupled to an emergent photon. Most importantly, we have shown that the contribution of the photon has a negative sign compared to the Wiedemann-Franz part of the thermal Hall conductivity. Naturally, there are many follow-up projects that remain for future research. For instance, it's interesting to investigate possible additional experimental consequences, such as for neutron scattering experiments, of the proximity of the magnetically ordered phase to a chiral spin liquid. Furthermore, as phonons are known to yield significant contributions to the thermal Hall conductivity, it seems worthwhile exploring the relevance of the physics discussed here to phonon-mediated thermal Hall conductivities, which can, for example, arise from a coupling between the emergent photon and the phonons of the system. Thanks for watching.